Let's do another states of matter phase change problem, and we'll deal with water again, but this one hopefully will stretch our neurons a little bit further. So let's say I have 500 grams of water, 500 grams of liquid water at 60 degrees Celsius. Now my goal is to get it to 0 degrees Celsius, and the way I'm going to do it is I'm going to put ice into this 500 grams of water. And my ice machine at home makes ice that comes out of the machine at minus 10 degrees Celsius ice. And my question is exactly how much ice do I need? So how much or how many grams of ice? So how much ice do I need to bring my and I'm going to take the ice out of the freezer and just plop it into my liquid. How much do I need to bring this liquid, this 500 grams of liquid water, down to 0 degrees? Down to 0 degrees. So the idea, I mean, if we just imagine a cup here, let me draw a cup. This is the cup. I have some 60-degree water in there. I'm going to plunk a big chunk of ice in there. A big chunk of ice. And what's going to happen is that the water, heat from the water is going to go into the ice. So the ice is going to absorb heat from the water. So the same amount of So in order for water to go from 60 degrees to 0 degrees, I have to extract heat out of it. And we're about to figure out just how much heat. And so we have to say whatever was extracted out of the water essentially has to be contained by the ice. And the ice can't get above 0 degrees. So essentially that amount of ice has to absorb all the heat to go from minus 10 to 0. And then also that energy will be used to melt it a bit. But if we don't have enough ice, then the ice is going to go beyond that and then warm up even more. So let's see how we do this. So how much energy do we have to take out of the 500 grams of liquid water? Well, it's the same amount of energy that it would take to put into 0 degrees liquid water and get it to 60 degrees. So we're talking about a 50-degree change. So the energy or the heat that out of the water, heat out of water is going to be the specific heat of water, have here from our previous videos, 4.178 joules per grams Kelvin. So it's 4.178 joules per grams Kelvin. And I have to multiply that times the number of grams of water I have to cool down, I have to take the heat out of. And we know that's 500 grams times 500 grams. And then I multiply that times the temperature differential that we care about. And just a side note, I use this specific heat because we're dealing with liquid water. Right? We're dealing with liquid water. Liquid water going from 60 to 0. So the final thing, I have to multiply it by the change in temperature. The change in temperature is 60 degrees times 60 degrees. There's a little button on the side of my pen. When I press it by accident, sometimes it does that weird thing. So let's see what this is. So this is 4.178 times 500 times change of 60 degrees. I could write, it could be a change of 60 degrees Kelvin or a change of 60 degrees Celsius. It doesn't matter. The actual difference is the same whether we're doing it Kelvin or Celsius. And that's 125,340 joules. So it's 120, so it's equal to 125,340 joules. So this is the amount of heat that you have to take out of 60-degree water in order to get it down to 0 degrees. Or this would be the amount of heat you have to add to 0-degree water to get it to 60 degrees. So essentially our ice has to absorb this much energy without going above 0 degrees. So how much energy can the ice absorb? Let's set a variable. The question is how much ice. So let's set our variable. Maybe we call it I. Well, let's do x. X is always the unknown variable. So we're going to have x grams of ice. Okay, and it starts at minus 10 degrees. So when this x grams of ice warms from minus 10 degrees to 0 degrees Celsius, how much energy will it be absorbing? So the temperature difference, so to go from minus 10 degrees Celsius to 0 degrees Celsius, the heat that's absorbed by the ice is equal to, so heat, I'll call it heat absorbed, is equal to the specific heat of ice water, 2.05 joules per gram Kelvin, 2.05 joules per gram Kelvin, times the amount of ice. That's what we're solving for. So times X, times the change in temperature. So this is a 10-degree change in Celsius degrees, which is also a 10 degrees change in Kelvin degrees. So we could just do 10 degrees. I could write Kelvin here just because, at least when I wrote the specific heat units, I have a Kelvin in the denominator. It could have been a Celsius, but just to make them cancel out. This is, of course, X grams, so the grams cancel out. So the heat absorbed to go from minus 10 degree ice to 0 degree ice is, see, 2.05 times 10 is 20.5, so it's 20.5 times X joules. This is to go from minus 10 degrees to 0 degrees. Now, once we're at 0 degrees, the ice can even absorb more energy before increasing in temperature as it melts, right? Remember, when you drew that phase change diagram, the ice gains some energy, and then it levels out as it melts, as the bonds, the hydrogen bonds are kind of start sliding past each other, and the crystalline structure breaks down. So this amount of energy the ice can also absorb, and so this is 0 degree. We do it in a different color. 0 degree ice to 0. I did it again. To 0 degree water. 0 degree water. Well, the heat absorbed now is going to be the heat of fusion of ice, or the melting heat, either one. That's 333 joules per gram. It's equal to 333.55 joules per gram times the number of grams you have. Well, once again, that's X grams. They cancel out. So the ice will absorb 333.55 joules as it goes from 0 degree ice to 0 degree water. So the total amount, or 333.55 X joules. Let me put that X there. That's key. So the total amount of heat that the ice can absorb without going above 0 degrees. Because once it's 0 degree water, as you put more heat into it, it's going to start getting warmer again. And if the ice gets above 0 degrees, there's no way it's going to bring the water down to 0 degrees. So the ice cannot get, not at this point, the water can't get above 0 degrees. So how much total heat can our ice absorb? So heat absorbed is equal to the heat it can absorb when it goes from minus 10 to 0 degrees ice, and that's 20.5 X, where X is the number of grams of ice we have, plus the amount of heat we can absorb as we go from 0 degree ice to 0 degree water, and that's 333.55 X. And of course, all of this is joules. So this is the total amount of heat that the ice can absorb without going above 0 degrees. Now, how much real energy does it have to absorb? Well, it has to absorb all of this 125,340 joules of energy out of the water, because that's the amount of energy we have to extract from the water to bring it down to 0 degrees. So the amount of ice the energy absorbs, or the amount of energy the ice absorbs, has to be this, 125,340. So that has to be equal to 125,340 joules. See, we can do a little bit of algebra here. Add these two things. 20.5x plus 333.55x is what? It's 354.05x. Is that right? Yeah, 330 plus 20 is 350. Then you have a 3, but then you have a 0.5 there. Yeah, 354.05x. That is equal to the amount of energy we take out of the water. And you divide both sides. So X is equal to 125,340 divided by 354.05. I'll take out the calculator for this. Calculator. And the calculator tells me, let's see, 125,340, the amount of energy that has to be absorbed by the ice, divided by 354.05 is equal to 354 grams, roughly. There's a little bit of extra. So actually, just to be careful, maybe I'll take 355 grams of ice, because I definitely want my water to be chilled. So our answer is x is equal to 354.02 grams of ice. So if I take, so this is interesting. I had 500 grams of liquid. And, intuitively I said, oh boy, if I have to bring that down to 0 degrees, I'd have to have a ton of ice. But it turns out I only need, what was the exact number? 350. So the liquid is 500 grams, about roughly half a pound, if you want to get a sense for how much 500 grams is. A kilogram's 2.2 pounds. So this ice is 354. So you actually have to have less ice than water, which is interesting because it seems like the ice isn't making that big of a temperature change. The ice is only going from -10 to 0 degrees, while the water is going all the way from 60 degrees to 0 degrees. So you're like, well, how does that work out? And the reason is because so much energy can be absorbed by the ice in the form of potential energy as it melts. So the heat of fusion, so if you talk about all of the energy that the ice is absorbing, most of it is due to the heat of fusion right there. So the ice can you can actually have 0 degree ice and it can still absorb this huge amount of energy just by melting it without even changing its temperature. Anyway, hopefully you found that reasonably useful.